This is lesson 4, the definite integral. This notation here, which is going to help us find the exact area under a curve, this sigma notation, is going to be very important. We're saying that the limit as n approaches infinity, and these are the number of subintervals of some function where the height of each interval, it'd be the function at some x value we will call c sub I, so we will have infinitely many of these heights, times the width of each of the subintervals of each of the rectangles. And when you add up, basically you're adding up all these infinitely many rectangles, you're going to get the total sum under the curve, because you're going to get the sum of all the areas of all the rectangles under the curve. Now, these sums are called Riemann sums. It's a very important thing. If you look it up, there's a whole history about the mathematician Riemann and these sums. And in these, remember, we're talking about rectangles. And the endpoints of the rectangles of each subinterval, meaning of each little rectangle, they're not necessarily the height of the rectangle. They're the two endpoints that create the rectangle, but they're not necessarily the height of the rectangle. The endpoints will be called the set of P. And so you always have that very first endpoint, or I should say the starting endpoint, that would be the first side of the first rectangle, and then the second one, so this would create your first rectangle from x sub 0 to x sub 1, and then from x sub 1 to x sub 2, this would create the second rectangle of some width, etc., etc., all the way until you have n endpoints from the very start at 0 all the way to infinitely many endpoints. The interval would be from A to B, meaning this x sub 0 is your A, and the very last endpoint, x sub n, would be your B. Okay, so there's always going to be one more endpoint than there are rectangles. Sample points are the x values for the height. Those are the c's. Those are called the sample points. And these will be exactly, however many rectangles there are, that's how many of these sample points there will be. So the function at c sub 1 would be the height of the rectangle, the first rectangle. F of c sub 2 would be the height of the second rectangle, etc., etc. Now here is a diagram where we've got some function. It's got a curvy thing going on here. And we just picked some random rectangles that have a height that intersects the function. These are random rectangles. They're not of equal width. They're not the same height. The endpoints themselves, x sub 0 and x sub 1, they don't necessarily go and touch the function. They could, but they don't have to. These are just random. I always look at this and think it looks kind of like a cityscape, a bunch of high-rise buildings in San Francisco or in New York City. And the main thing is these buildings, these rectangles, have to intersect the function curve somewhere. Where do they intersect it? Well, at this point, c sub 1, this is the height to the function, which is the height of the building. And so you can see each one of these rectangles has a particular height, and the width of each of these rectangles, which is not the same, these are all different widths, would just be the distance from x sub 1 to x sub 0. You'd subtract this number here, whatever that number is, subtract the one that's to the left of it, and that will give you the width of that building. And so to figure out the area of this building, this pink building, you would take the height, which is f of c sub 1, the function at c sub 1, times delta x sub 1, and that would give you the area of this pink rectangle. To calculate the Riemann sum, which is to calculate the addition of all of these areas, this notation, very important, this is a Riemann sum notation. It says we're going to do the Riemann sum of the function f, where all of our endpoints are the set of P, and then we have all of our sample points, these C's. Okay, so we have our function is called f of x, our endpoints are all of our x's, and in this case up here I have 5 rectangles, so I have 6 endpoints. I have 5 rectangles, so I have 5 sample points that I'm using to find the height of all of those rectangles. And I use this to find the complete Riemann sum. And to do that, I take the height of the first rectangle times the width of the first rectangle, plus the height of the second rectangle times the width of the second rectangle, plus, and I keep adding each one of these heights times widths, which is areas of rectangles. So, the definite integral when we're going to calculate it out, here's that notation, sigma notation. I'm saying that the limit, as we have infinitely many subintervals, so they're getting narrower and narrower and narrower, and we're doing all those heights times widths, that is the same exact thing as the definite integral. So we're going to have the integral from the beginning of the closed interval A to B, these are our limits, the endpoints of a closed interval, of the function dx. Because remember, this is the width and this is the height, and we're going to be adding up from a to b. So the integral from a to b of f of x with respect to x. It's signed area, and that's important to recognize, that when we talk about signed area, that when we're talking about area that I would have above the x-axis up here, that's going to be a positive area. If I have area below the x-axis, it's going to be considered a negative area. So this kind of area is signed similar to how velocity is signed speed, that we have negative miles per hour and positive miles per hour depending on the direction of that we are traveling. Well, with area, we have positive area when we are above the x-axis, and we have negative area when we are below the x-axis. So that's something that's important, that we sometimes have to divide up our diagrams or our functions to talk about positive and negative areas. Now here's a diagram of some function, and it's got a lot of linear things, and this, you'd even say, well, is this really a function? But it's a relationship, and it has all of this area here that I'm going to talk about that's shaded in. I want to find the area of it. So what is the area of each triangle, and what is the total area of the shaded region? Well, you would end up calculating the area of this triangle, and so you've got 2. The base is 2, the height is 4, so the area of this triangle is 1/2, 2 times 4. This triangle here, we've got a base that is 3 and a height that is -6, so it's going to be 1/2, 3 times -6. This one here, we've got a base of 3 and a height of 2, so we're going to have 1/2, 3 times 2. And so when we do that, you have a 4, a 9, and a 3 for each of those areas. If I ask you for what is the total area of this, you're just looking at this as a geometry picture, you would say that it has a total area of 16, because you would just add up each of these areas. But signed area, well, this is going to be positive 4, this is going to be positive 3, but this area here is going to be -16. And therefore the total signed area of the shaded region is -2. So in this particular problem, we have this shaded region and this shaded region, and if you look at it, I don't have numbers on here, but this is a semicircle, and this is an identical semicircle, and because these are semicircles of the exact same height, the same width, this would be a positive, whatever the number is, +7, or whatever the area is here, this would be negative. And therefore, the total signed area, because integrals have signed area, would be 0, because my positive region and my negative region are the same size. Here, calculating these different areas, and I'm telling you here, so we don't have any numbers, that this region has an area of 3, this region has an area of 7, and this region has an area of 1. And this, since this is integrals, which is signed area, I would do 3 minus 7 plus 1, and we get a total signed area of -3. And remember that integrals always give us signed area. So let's look at an integral, but let's look at it in two different ways. One, we're going to look at it geometrically. So here is an integral from 1 to 4 of this function x plus 1, which is a linear function. So we draw the line x plus 1, but we only draw it between 1 and 4. Now the line, of course, would continue on in all these, before and after 4, but we're only interested in this line between 1 and 4, and it would be the area from the x-axis up to that line. And geometrically, we could look at this and say, well, it's a trapezoid. But you'd have to remember your formulas for the area of a trapezoid. It's a lot easier for us to say, well, if I just draw a horizontal line right here, I've created a triangle and a rectangle. And it's easy enough to add up the area of a triangle, and we can see that the one side of that triangle is 3, and the other side of that triangle is 3 also. It's not drawn to, the x and y axes aren't the same scale. So this is 3 and 3, so 1/2 3 times 3, that's the area of the triangle. This is 3 by 2, so 3 times 2, adding all that up, we get 10.5. And so just looking at it graphically, or, geometrically, we can add up those areas. We can also do this on our calculator. Our calculator, under the math key, there is an integral symbol. If you have the old style that does not have pretty print, it would be in this format here, where it's function, variable, lower limit, upper limit that you would plug in, just like I did here. If you have the nice pretty print calculators, you're going to get the symbol, and you're just going to plug it in, so it looks just like it does up here. So you'll type it in just the way it is, and you'll hit enter, and you will get the same value as we got here, 10.5. I want you to do these 5 problems and post it to Google Classroom, and then come back to the video and watch the next video for the next lesson.